Hey, physical science kids, welcome back. This is Waves Part 2 notes. Okay, so we're going to talk about some things on here, actually, like the anatomy of waves or how it's all constructed and things like frequency and a wavelength. So let's get started. First off, we're going to watch this little video here all about nodes and antinodes, and we'll talk about that here in 1 second. Here we go.
Whoa! Now, you may have seen a Rubens tube before. That's basically a pipe with a bunch of holes in it, and you pump in a flammable gas and light it on fire. So you basically create a row of Bunsen burners. What's really cool is to play some sounds into the tube, and you can actually set up standing waves. That is, there are patterns of the vibration of the air where there's a lot of vibration in some parts and not very much vibration in other parts. Now, that affects the flow rate of the gas inside that tube into the atmosphere, and so it affects the height of those flames. So basically, you can visualize the standing wave pattern. I'm currently in Denmark with a team of physics and chemistry demonstrators who have taken this experiment to the next level. They've actually created a two-dimensional Rubens tube, a whole plane of Bunsen burners, effectively. How many holes in this tube?
2,500.
2,500 in this pyro board.
Yeah.
So we're going to see 2,500 little flames.
Yeah.
So do you want to light it up?
Yes, I really want to light it up.
Why did you make this?
Because we really like the Rubens tube, but then we thought, when you put on more fire, then it always gets better. And let's just turn it down. And then we can just try to find a standing wave. So this is below the standing wave.
Cool.
Yeah, so it's really difficult to see it. We need a little bit.
So what are we seeing here?
So what he's going to try to explain is this is like the top of a wave, and you have to imagine the flames are kind of down below the board here. So this would be the bottom of the wave. The top of the wave is called a crest, and the bottom is called the trough. And you'll notice that it comes back up to another crest. Okay, but it's not like there's nothing here. The flames are actually below.
Pretty much like the standing wave on the Rubens tube. It's just in this direction. And it's the lowest frequency that makes a standing wave in this box.
So this is like the fundamental.
It's the fundamental.
Can you show me what happens when you vary the volume a little bit? Whoa.
Now that's going to become very important here, is that with the volume or the energy increase, like we talked about in the last section of notes, notice it just got taller. There's not more or less waves. It's still the same number of waves. There's a crest, a trough, and one crest. Okay, so a total of two crests, or a half a crest, and one trough, but it got much taller. So we have to envision that the flames below the board actually got taller as well, but just in the negative direction.
That was awesome. Okay, should we try to find another standing wave?
Yes. You can see it. You can hear it before you can see it.
Whoa.
Notice there we're going to have crest, 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 trough, trough. So did you notice the pitch has gone up, but the crest, the number of waves has increased.
It's weird. With the microphones, I can actually hear. Like here, I'm in a node. And then here, I'm in an antinode. Here, I'm in a node.
Because you can measure the sound pressure.
I can hear it. Like here is very much antinode.
I never thought about that.
This is a node, and you guys can hear it.
Yeah, that's true.
It's incredible.
Wow.
The flames must be coming out in the antinodes.
The flames are coming up in the antinodes, yeah.
And you can even hear it.
Yeah.
That's
Nice
incredible.
that you can do that. Yeah.
That is awesome.
We just learned something.
Now, what happens if we try to go higher frequency?
Yeah, have something. Oh, that's a good one.
That is crazy. We're right in the antinode.
To your ears, okay?
Oh, God.
My ears are hurting now.
That was painful. Why don't we try to put something more pleasing to the ear through the speaker and see what happens?
I think that's a good idea.
Yeah, let's put some music on there. You ready?
Go.
All right. Well, the video goes on for a little while longer. They play some more music and everything like that. But what's kind of crazy is the idea that that technology you've probably seen um, in some music videos, and like if you go to concerts and stuff, that the flames kind of play with the music, not just shooting out fire, but actually literally dancing with the music. And this is a little bit of an older video. It's about 5 years old now, and I feel like it's a lot more common at concerts now than it used to be. But that company that did that study, they ended up selling those to like performers and stuff, and that's kind of how they fund the rest of their science. All right. So this is where you'll need to make sure that you watch during class with this idea of a slinky wave, and we're going to mess around with this slinky in class and kind of help understand that. But anytime the slinky is just resting there without moving, we assume that that's called something called the equilibrium or rest position. A pulse is like if you've ever played with a slinky and you flick it and you see that pulse run back and forth, that's what pulse or pulsing a slinky back and forth is. All right, this is called something. This is called a longitudinal wave. That pulse is moving along the wave. We say that it is moving parallel with the wave. All right, a transverse wave actually moves perpendicular or up and down. And again, we'll need to look at the visuals when we do the notes in class. But the idea is even though you're moving a slinky up and down, you're doing transverse up and down, you'll notice that the energy stays in the same spot. That particle stays in exactly the same spot. So longitudinal waves, a great example of a longitudinal wave is a sound wave. It moves in a direction. It has a pulse that moves in one direction. That's why somebody speaking directly at you is different than someone speaking in a different direction. You can still kind of hear them because of things reflecting off of stuff. But in essence, if it's speaking directly at you, you hear that different. And we say it moves parallel again. Again, transverse waves, we say, move perpendicular, but notice those patterns, even though they're moving up or down, you'll notice they end up in exactly the same spot, kind of like a stadium wave. If you stand up and you go, woo, and you sit back down, you didn't move seats, okay? You stayed in the same spot, right? Ocean waves are transverse waves. You move up and down, but you really stay in the same spot, okay? Currents tend to push you underneath, but like if you ever seen like a bird sitting on the water, they're kind of just moving up and down. And that's why people get seasick, because you're in this circular motion, okay? Some of you might be looking at that right now going, oh, I'm getting a little woozy, okay? That happens. All right, here's a great picture of it. A longitudinal moves along the wave, okay? Perpendicular, transverse move up and down, or perpendicular to the motion. All right, so anatomy of a wave, okay? So again, the dash line is what we refer to as the equilibrium line, okay? The dash line is the equilibrium or rest position. You have to imagine if this wave is moving up or down like it is, if we just let it go back, they would all end up on the dash line. The tops of the waves are called the crest, and we call like a hill, we say the crest of a hill, all right? The bottom are troughs. Does anybody know what a trough is? Anybody heard that word trough before? Well, troughs refer to like what animals eat out of. It's like the bin where like with pigs they would dump food in there and they would eat out of them. So that's why they're called the trough. Amplitude, probably one of the most missed things, okay? It is the height of the wave. It can be in the positive or the negative, but it is off of equilibrium. A lot of people will say the height of this wave is like from A to D. No, the height of the wave is from equilibrium, because imagine this thing is moving up here. It could move back down here, but it will never have that entire height. It's only from equilibrium up to or from equilibrium down to its maximum point. Wavelengths. Okay, wavelength is from one point on a wave to the next consecutive exact same point. So a lot of times from a crest to a crest is a wavelength. That's probably the easiest. Where else can you see a wavelength on here? One would be D to I, or a trough to a trough. That would be a wavelength. Okay, that would be Oh, goodness. That would be one wavelength. Where else on here? Some people are saying, well, from C to H, that's another wavelength. You'd be right. Because look, you're coming down the hill, coming down the hill. Now, a lot of people will say B to E. That would be incorrect. That would be a half a wavelength. Because look, we're coming down the hill, then we're coming up the hill. It's got to be the same point. So we go down the hill. The next time we go down the hill is at G. So B to G, and then up the hill would be E over here to J. Okay, so a lot of people will say B to E, but that would only be a half a wavelength. All right, so we mentioned this in the video. Nodes are these areas right here, these areas where basically it's not moving. Okay, it is kind of moving, but it's almost like that piece of matter is frozen in time there, and you'll see that during a demo. But those are called nodes. So the antinodes would be where the crust and the troughs are. So there you go. With no amplitude's the way to think about it, where there's no amplitude. All right, let's take a second here. See if you want to pause the video and see if you could label these things. All right, coming back. A would be A saying from this point to this point, and that would be a wavelength. B is actually from not equilibrium, but from the bottom of a wave to the top of a wave, the two extremes, that would actually be 2 times the amplitude. C is saying from this point to this point, or really I'm kind of focusing on these points in general, and that's why I say that's a node. If you said half a wavelength here, you'd be right also. D is amplitude, how far something is from equilibrium to its maximum displacement. And then finally, E is a half a wavelength from the top to the bottom, and that would be a half a wavelength. Again, just showing you this, even though this is a transverse wave and this is a longitudinal wave, it still follows the same pattern. All right, here we go. Frequency of a wave. The frequency of a wave is how many waves are created in 1 second. Okay, it is measured in hertz. If you think about the word frequency, it's literally asking you, like if you've heard that word, like how frequent you go somewhere, it's basically how many times you visit in an amount of time. Well, the amount of time we're going to say is 1 second. So it's how many times you visit something in an amount of time. So if we look at this wave right here, if we imagine that this is 1 second, we would say that this wave, the frequency is a 1, 2, 3, 4, 5, 6. So we could say that the frequency of this wave is 6 hertz, that there are 6 waves for every 1 second. Okay? And this is the equation. Frequency is 1 over big T, and big T is actually called the period. Now think about this for a second. Okay, let's get this out of the way so you can see this. But think about this for a second. Period is an amount of time. This is an amount of time. Just like in school, you go to school for 7 periods or 8 periods. Okay, it is an amount of time. Well, this is literally measuring the amount of time it takes to make one wave. This is how many waves. Frequency is how frequently you visit in an amount of time. So if you go to the mall frequently, to me, that would be something like once a week. Well, for some of you, that might be 2-3 times a week. It's how many waves there are in 1 second. Period is the amount of time it takes you to make one wave, or how much time it took you, okay, to make this one wave. Okay, so for example, if we said that this is the period of a wave, well, let's just pretend again this is 1 second again. Well, how many waves are there? There are 1, 2, 3. So your frequency would be 3 hertz. Okay, your frequency would be 3 hertz. All right, but that's not what we're asking. Okay, we're asking about period. Okay, how long did it take to make this wave? The frequency is 3 hertz. Okay, the frequency is 3 hertz. It's 3 waves for every 1 second. All right, but the amount of time it took to make one wave is actually a third of a second. If this is 1 second, there are 3 waves in every 1 second, or if we take 1 divided by 3, that would be a time of 0.33 seconds, or 1 over 3. I know it's a little confusing, but we'll work through that. So here's an idea. Just looking at this, which wave has a higher frequency, the top or the bottom? The top has a greater frequency. There are more waves in the same certain amount of time. Which wave has a longer period, or which wave takes longer to make a wave? And that would be the bottom wave. So here's a little way of looking at it. Suppose I wiggle a slinky back and forth and count 6 waves pass in 2 seconds. What is the frequency and what is the period? Or how many waves are there in 1 second, and how long did it take to make just one wave? Well, we need to look at it. Remember, frequency is the amount of lambdas, and lambdas, I should have said lambdas, is wavelength, okay? Lambda is the symbol for a wavelength. I guess I should have wrote that earlier. I apologize, okay? Sorry, I can't write on here. It's hard to just write words, okay? There you go. So if you look at that, how many lambdas per second? Well, in 2 seconds, there's 6 waves. Let me get this out of here again. In 2 seconds, there's 6 waves. But in 1 second, that would be 3 waves, okay? Right there. And you could push that in there and figure that out, okay? Now, period. How long does it take to make just one wave? Well, if we split this up, this is a wave, there's 1 wave, 2 waves, okay? It only takes a third of a second to make each wave. So for example, we can plug and chug it in there, or we can just do that systematically. The wave speed equation, okay? Again, we'll talk about this in class, but the idea is if we need to understand that the speed of a wave, the equation for speed or velocity of wave is the frequency times the wavelength, okay? And that's called the wave equation. So that's something we may just need to know, okay? We're going to do a lab about this. Okay, now these next couple slides, the next 3 slides are actually a homework, and then we're going to work through them together, and we're going to work through them, and then we're going to do a little lab, and we're going to do some practice, so we should be good. If you're confused, that's okay. This is a very complicated subject. What we need to make sure that we do, though, is ask questions. There are never enough questions. If you're ever confused about something, make sure you ask. Until next time, hopefully you're in class and you can ask those questions right away. But if not, you'll have to reach out to me and get those answered. Till next time, talk to you later. Mr. Tima, out.